We're going to talk about DSC analysis. So DSC is differential scanning calorimetry. Hopefully, again, you've done this in Engineering 45, so you're used to the technique. Essentially, what we have is you have basically this pan. One is a reference pan. Another is a pan with some sample in it. Usually, it's a powder sample. So sample pan. Usually, you want basically 2 to 4 milligrams of your powder sample. You want to compress the sample. This is usually it's an aluminum or it could be a ceramic pan. Basically, you don't want the pan to melt, but I'm getting a little bit ahead of myself. So in this DSC apparatus, we have basically there's some thermocouples hooked up here. So thermocouple. And basically what this technique does, it allows you to kind of measure the temperature of your sample pan and your reference pan and the corresponding and the heat flow. And then you could determine essentially the thermal performance of materials, a function of time and temperature. And you could find some of these properties like specific heat, CP, melting point, TM, boiling point, glass transition temperature, TG, very important to us, heat of fusion, reaction kinetics. You could find out your T sub C, your recrystallization temperature, et cetera, et cetera, et cetera. So you're going to have basically this is a heat flux system. So we're going to measure. So we're going to create a plot which is delta H. We're going to measure the heat flow between these two different samples. So the differential heat flow. So delta H, or we know that this is kind of equivalent to D, the partial or the imperfect differential of Q. So our heat flow. Again, this is just heat flow. And this is going to be in units of, this is going to be in units of milliwatts. So that's what we're going to create a plot of heat flow versus temperature. So we're going to increase or decrease temperature, and we're going to see what is the difference as we increase, as we have this sample become, again, we're going to raise the temperature. And we're going to have this pan be the same temperature as this pan, and we're going to look at what's the difference in the heat flow required to reach those temperatures. So again, differential heat flux between a reference pan, again, empty, sealed aluminum pan, and then a sample pan. So again, separate stages, thermoelectric sensor. Again, temperature is raised, linear rate. Again, usually we can go between, usually we do 10 degrees K per minute. But you can go much faster, slower, and again, that's going to change the TG as well. Excellent. Reference pan, heat flow, difference between, again, the sample and reference pan is measured. It measures the temperature difference using the thermocouples at their respective stage. So, again, it's looking at, it gives you this quantitative information about heat absorption or exothermic heat release. So remember, endothermic, we're absorbing heat. Exothermic, we're releasing heat. Typically, you'll see endo on top here. So if it's endothermic, if we're absorbing heat, it's going to be a value at the top. And then if we're releasing heat, exo is kind of on the bottom. That's typically how these kind of peaks are shown. And then you'll kind of see something that could look like this. So increasing a change in slope, and maybe this. And basically from these kind of peaks and valleys, we're going to be able to kind of determine essentially latent heat of melting, TG, et cetera, et cetera, et cetera. So very, very, very important tools when you're characterizing essentially the quantities of a polymer. And again, we can kind of deduce phase transitions because we know that dG equals minus SdT is VdP. We're going to be at constant temperature here. So if I want to do the first derivative of Gibbs, that's just going to be equal to my enthalpy. So if I have a first order phase transition, i.e. melting, and I know that I could also relate ES equals Q to T, which I also know that dQ is approximately equal to delta H. So again, the heat flow versus temperature is going to be the first derivative of Gibbs. So I'm looking at, again, this first derivative of Gibbs. If I plot heat flow versus temperature. So if I see a discontinuity, I'm going to see a first order phase transition. The second order phase transition would just be the second derivative of Gibbs with respect to temperature squared, which is basically going to be equal to the kind of heat capacity over Tm. But again, you can look that up from your thermodynamics notes. So we'd see a discontinuity in the second derivative, basically in the specific heat if we plotted that versus temperature. But you can kind of deduce a second order phase transition by a change in slope. So this will be our TG. So this is TG. This is going to be our TM. If I integrate this peak, this is going to give my delta H of fusion or melting. So the enthalpy basically absorbed during kind of the melting process. And again, if you see a peak basically below it, that's an exothermic peak. But anyways, we're going to get into that in just a second. So this is going to really tell us a lot in terms of if a polymer is amorphous, crystalline, and other different kind of properties. So let's go ahead and look. So these are kind of two different curves that can occur for an amorphous and crystalline polymers. So which one's amorphous, which one's crystalline? This is amorphous. Why is this amorphous? Because we only see a TG. But you can see here for our crystalline or semi-crystalline material, we see this change in slope, which is our TG. We also see this, this doesn't occur for all polymers, for all semi-crystalline polymers, but this is the delta H of crystallization, and this is TC. This is your crystallization temperature. As you raise temperature, you're initially in your frozen state, right, below TG. But once you go above TG, the polymers are able to kind of move around and start to fluctuate, move collectively, and sometimes that could lead to crystallization or recrystallization. So that's kind of the recrystallization step. So that can occur, and recrystallization is an exothermic reaction. So we are releasing heat as we crystallize our material. But we need to absorb energy in order to melt. So again, later on, then you hit your melting temperature. And again, these are still first order phase transitions right there. So again, you want to be aware, endo, exo, again, releasing heat, melting is an endothermic reaction. We are absorbing heat, and then TG, again, look at where that's going up. And again, you can kind of tell the slope of this is going to be positive. Why? Because again, TG, we have to absorb energy in order to kind of, again, move around and wiggle in our material. We could also distinguish between a thermoplastic and a thermoset. So this is, again, our semi-crystalline polymer. Look at here's TG, it's TC, et cetera, et cetera. But if we have a thermoset polymer, we know that thermosets need to cross-link or cure. And cross-linking is an exothermic process. So once they, again, when you mix, you kind of tell it. If you've ever mixed epoxy, it kind of gives off a little bit of heat, really, really slightly. But if you mix it, and you're stirring it and you're mixing, it gives off a little bit of heat. So it releases heat as those interactions are kind of formed. So cross-linking is an exothermic process, as you can kind of see here. So thermosets still have a TG, but they also have this, again, the curing process. So this delta H of cross-linking. So it's a nice, again, all these kind of different ways that we can kind of determine, again, not only where our TG is, what's our enthalpy of melting. We could also figure out the percent crystallinity by looking at our delta HM divided by the delta HM, naught, where this is basically the theoretical delta H of a 100% crystalline. So if I have 100% crystalline polymer, I can, again, that theoretical data point from literature, I can just take what is my actual or true value for my delta H of enthalpy of formation, or enthalpy of, of fusion, or enthalpy of melting, and then divide it out by the theoretical value, and I can get my kind of percent crystallinity. So these are kind of all these different values. You can see, again, look at the power from one single curve. I can tell whether I'm thermoplastic, thermoset, crystalline, amorphous, what's my TG, what's my TC, what's my TM, all just from this single curve. So it's a very, very, very extremely powerful technique that we can kind of see. So again, we're looking at discontinuity, the first order of free energy. Again, function of temperature. Second order transitions will be in, again, second order of Gibbs. So we're plotting, again, this delta H versus T. We've kind of already talked about this. So again, glass transition temperature, that's our first peak. It's a second order phase transition, so we're going to see, again, a change in slope there. TC, again, this is first, it's an exothermic reaction, so it's some solidification or recrystallization process. Again, we increase mobility, and so increased mobility, we can basically encounter the change and then fold. And then finally, endothermic reaction, melting, again, does not break carbon-carbon, but secondary interactions. So we know that for amorphous polymers as well. And then finally, thermoset does not undergo melting because permanent crosslinks. So we don't see, that's another one of the key features. We don't see this melting point because, again, we don't melt a thermoset. Thermoset does not undergo a melting temperature. Those are permanent crosslinks, so you would denature. So again, but we have this exothermic peak because energy required, or energy released essentially, released to cure or crosslink a polymer. So, so it has to cure and form crosslinks. And when it happens, you release that heat. So that's about it. So DSCs are really, really kind of useful, important characterization techniques. What happens, for example, what if I ran a DSC curve? So let's say I have two DSC curves, same polymer. So I have delta H. I'm going to always label endo, exo. You could be given curves that might be flipped, so be careful of that. What if I have a polymer like this? Oops. So it's fully amorphous. But then I also, again, ignore the magnitudes there. I'm running the same polymer, same exact polymer here. But for one run, I get this TG, and another run, I get this TG. Usually you just find TG at the center of this kind of slope. So what can cause the difference here? Processing-wise, the polymer is exactly the same. So what can I do? Well, we know in this DSC curve, I basically I have a heating and cooling rate. So cooling rate. So I have a heating rate and a cooling rate. So what if my heating rate, if I'm going up, what if I heat at 10 degree K per minute versus 1,000 K per minute? What do we know, looking back to our notes, about how our TG varies as a function of cooling rate? Faster cooling or faster heating, we have what? Or actually, let's think of the cooling rate, actually. Cooling rate and heating rate. So faster cooling, faster heating. You see this change in TG, right? So if I cool extremely, extremely, extremely fast, what happens? I have a higher TG. So a higher cooling rate, faster cooling, I'm going to get a larger TG than here. So this could be cooled at this rate versus this rate right here. So one thing to think about, again, as you kind of process or encounter problems with polymers. So I will, that is it. So next time we are going to get into polymer dynamics. So kind of diffusion of polymers, rectation, Rouse regimes, and some really, really cool interactions. So I hope you liked the video. Let me know if you have any questions. Thanks. Bye.